So today we will talk about recurrent neural networks. First, we will talk about sequence data. What kind of sequence data do we have? What kind of tasks do we need to accomplish? Second, we will talk about autoregression and kinds of autoregressive models. Then we will discuss a basic recurrent architectures such as RNN, GRU, and LSTM. On the next lecture, we will talk about transformers, zero-shot learning, and LLMs. Recurrent neural networks built for sequences. As an example, I took a trading data. You can see here an ask quote, transaction price, as well as volume and depth of bit depth and quoted spread. This architecture is taken from the paper Deep LOB. Here you can see a combination of LSTM and convolutions. So the time series data from trading first convolved in inception manner and then passed to an LSTM recurrent unit. Convolutional block helps you to extract more granular features, and LSTM as a recurrent block tracks dependency of the future data points from previous. In this way, you can predict price or volume or depth or ask what or whatever for future, of course, with some accuracy. Second, you can have a sequence of images and caption it by recognizing a type of action which object performs on a series of images. As an example here, you can see images where a giraffe, it's in a jungle and you have series of images and object is detected in each of the images, and then a series of crops is formed, RNN generates action and object, captions and series of images. RNNs can also generate data, of course. First, they trained on some music data, and then they capture the music model, and then they can generate, if switched to a generative mode, they can generate music that sounds like something that they've been trained on. RNN models can perform speech recognition. Here you can see how speech is transformed to a histogram of frequencies, and then it passed to a recurrent neural network, which outputs text. Again, that's the results of a paper. Another one application of recurrent neural networks are machine translation. It's a sequence-to-sequence translation with attention. You can see here that encoder-decoder architecture, you have inputs and outputs, a multiple-to-multiple symbols are translated. Recurrent neural networks can be applied to a DNA sequence analysis, identification of a transcription factor binding sites. You have a DNA sequence here, and this model detects a particular region which performs a transcription binding site. Let's talk about autoregressive models. First, there are 5 types of inputs and outputs in sequential modeling. You can see all of them in front of you. The sequential modeling can be one-to-one in terms of inputs and targets. Think of them as X and Y. One X, one Y. Where can it be? For example, in trading time series, you have one tick and you have one price, right, for this time tick. For the second time tick, you will have another price level. Then you can have one-to-many, one input and then generation, right? Then you can have a many-to-one. Think of some time series or of that giraffe, like series of images with some action performed, and your network have to read multiple images and output only one class. What kind of action has been performed on this series of images? You can have many-to-many. in two implications. One is where number of inputs and number of outputs are different. For example, translation of English to French. You can have the same sentence, like 7 words in English and 15 words in French, and vice versa. That's why this architecture allows to have any number of inputs and outputs, of course, in a reasonable range. Then you can have a many-to-many, like one-to-one, one input and one output, which is a simplified case of general many-to-many case. So all the further architectures that we will discuss, they fall into one of the types of autoregressive models. Let's talk about the general architecture of RNN. Here you can see a simplified notation of recurrent neural network as a hidden state. That's actually your neural network with input and output. Let's say it's one-to-one. Your network, your H hidden state, it remains the same. It just applied multiple times for multiple inputs and outputs with time step denoted as T. T can be 0, 1, 2, 3, etc., etc. The idea is that you apply the same network for each of the inputs, or for each pair of inputs and outputs. Each pair of X and Y are called time step T. Yeah, an idea is that this kind of networks can work on this arbitrary lengths of a sequence. The overall idea was to somehow save and decrease amount of weights by reusing them. This notation that you can meet here, and actually you saw here, is nothing else rather than repetition of application of the same network to multiple inputs and outputting multiple outputs following the sequence of values. So don't be confused. This is one network applied to multiple inputs. Pay attention that hidden state is the same architecturally. That means here will be the same 3 layers, each layer like 512 neurons. But the weights and the state of its hidden state will change. Each time step, we will perform forward propagation and backward propagation. So strictly speaking, each time step will have different weights in the training mode, but the same architecture and the same network. So if we denote our network with weights, then you have 3 sets of weights. You have weights for inputs, let's call them W subscript XH. You have weights for outputs and weights of parameters, metrics of parameters, WHO, and you have weights for activations or hidden state. Let's denote them with WHH. If we unfold it, we will have the same weights applied at each time step during forward propagation, then they will be updated during backward propagation. If you are to build a multi-layer RNN, for example, 2 layers of LSTM, 2 layers of RNN, they will look like this. You will have one RNN layer and another RNN layer. And the first RNN layer will act as providing inputs to another RNN layer. So the inputs for the second RNN layer will be the outputs of the first RNN layer. Nothing very difficult. Sometimes it helps, sometimes it overfits. Backward propagation of recurrent neural network is called backpropagation through time. Why through time? Because first we have to unfold all the steps of this hidden state for all the elements of the sequence, and only after we reach the last element of the sequence, we can calculate the loss and backpropagate, starting from all layers from the last step. Then we will have the activation that we will be backpropagated to previous state. And then we will backpropagate through all the layers of this, like it's the same network, but we will do once again. And in the same manner until we reach the very first step. And this will be the one epoch of training any kind of NNN. I think you already feel how it is different from CNNs, right? CNNs, they backpropagate only once the network, right? And then you have next epoch. Also, the drawback of this is that it is much harder to parallelize RNNs since of their recurrent nature. And their effectiveness, like if you run them on GPU, they will be much lower than CNNs. This is because you have to cache all those intermediate gradients until you reach the beginning of the sequence. You have to cache all those states until you start backpropagate. Why do you need to transfer back the activation? Because now activation is another set of weights. You can see WHH is one of the important weights. These are the weights that are applied for activations, like hidden states outputs that are transferred to hidden state. You will say, hey, wait a minute. You just said that this is the same network, and now you say that this network transfers activations to this network. Doesn't it mean that we transfer the activations to itself? Yes, exactly. We are transferring activations by applying learnable weights to the same hidden states that it has been outputted from. Okay, so this is the secret of steps. This is how we reapply the same network for multiple elements. Now, the result of that is that previous state of the hidden state, it keeps information about previous steps and somehow accumulates until the last step. So we can say that at this step, network has seen all the elements before the last one or any one and bears some information about them. And that will be true. But we have to clarify it a little bit that the deeper the network, the longer sequence and the longer memory it can have. The simpler the network, the more it suffers from forgetting previous elements. The less context it can keep. Now let's talk about graphical representation of vanilla RNN. So the basic RNN in front of you, it is made of the following components. First, you have this like block, which is your like network. Here it is depicted in details. XT is one element of your input, one word or one symbol, depends on how you train it. And it has a shape of dx, like 1. Then you have your network is here with its activation. You have hypertangent activation, and you have multiple inputs. Pay attention. This is all the secret is here. So your input actually is not only your X, which is the X, but it also added something that is called DH. DH is your activation from previous step. This is the output of the same network after activation passed to itself. After we multiply, add everything, we take the same output and we compare it with target, calculate loss, and we pass the raw activation to the same network to the next step. So this output like comes here at the next step to the same network. Why? Because this is information about our previous state. So the input to the neural network layer with some nonlinear activation are twofold. First, like our X, second, activation from previous step. It's just concatenated. Here you can have a formula, HT, your activation output, activation of this hidden state, is equal to hypertangent, like this activation function, and inputs are W. W are concatenated weights of hidden state, this one. This is the rate with which we take into account information from previous step, previous elements, because they are summarized here in this state. And C, comma, plus DH plus DX. So this is a concatenated activation and input. So these are the shape of the weights and multiplied by activation and XT, see? Plus bias. So those are W and B are learned parameters, and H, T-1, XT are inputs. Autoregressive models. Language model. In front of you, you can see how this concept, this architecture that I just described can be applied to some toy problem. Let's say we want to generate text. To generate text, we need to learn the structure and the interdependencies of the letters inside the text. So this is some piece of text is shown, and this network takes as input previous symbol and outputs next letter in the word. So it's a word level language model. It can generate words. See, it can take previous word and predict next symbol. See, A is a symbol, then it takes A as an input and predicts next symbol, it takes C and predicts next symbol. So this network generates words. Those are outputs and those are hidden states. The idea is that hidden states, which are sets of weights, become a model of this word generation. Now let's talk about what we put where. So you have X, which is every symbol, and you have hidden states from previous element. This is a fully connected layer with some activation function. So your neural network, this is your neural network. Then your neural network outputs activation. We compare this, and activation in this case will be a softmax from your vocabulary. Your vocabulary is like 30 letters. It will be a chance that the next letter is one of them. So you compare it with the ground truth, which is like A, and you compare, is it like letter with index like 16 or the index that you output, right? And then you have loss here. And then you pass this activation to the next layer. You concatenate this raw activation with your input, and this is the input to the same network, but then its next step. You can see formulas here. Here is the declaration of RNN. So what I just told you, let's take a look how it is implemented. So you have RNN, you have inputs, states, and parameters. Parameters are weights for inputs, weights for activations, biases for activations, weights for outputs, and biases for outputs. State is hidden state, is a set of weights of our network. CH, this is H. Actually, this is a set of weights of this network. So we can load the state of the network. If we don't want to, if we want to load some pre-trained network, we input here its state. And now we travel over all our inputs. For X in inputs, X is every letter, like X, like M, A, C, H, I, N. So for these letters, now we calculate for every step, every element in a sequence, we calculate activation, that's activation function, hypertangent, which takes as an input matrix multiplication of X and WX, plus the same of activations and weights for activations plus biases. That's it. And then you calculate Y's. It's predicted outputs. See, you multiply other set of weights for outputs. You multiply with activations, H, the one that you predicted here, and you add biases for outputs. So these weights, W, HQ, and BQ, they are here. W, HQ, and BQ, they are here. The others are shown. It's WHH and WXH. See, WHH and WXH. Then you add it to outputs and you concatenate outputs by some dimensions. And then implementation of RNN model. So this is the RNN block. And this is the RNN model implementation from scratch. You have constructor function. Vocabulary size is number of elements in your sequence. Like here, it will be like 30 or 32 letters, depending on the kind of language that you use. Number of hidden layers. Then you have parameters. And you initiate state, and you can pass here the forward function. One hot is how your inputs are encoded. Like you can use here different function, but it's the simplest one. One hot encoding is representing each of the letters because you somehow have to feed your network with a letter, and you cannot like put a letter. Here we have represented as a number, and the way in this case, the way to represent it as a number was one hot encoding. One hot encoding is you say what is the index of this number in your vocabulary. You pass a vector of 30, like 30. There will be like 29 zeros and one at the place of its index. So you transformed your inputs as a one hot vector, and you passed it to a forward propagation function. Remember, we saw this function before, but it took only X and parameters. Now it takes a little bit more. It also takes state. The state is this. The state is what you pass between your steps by preserving weights of your hidden state. And you have a begin state is the initialization of your state. You initiate it with a proper dimensions and in which device it has stored its weights and perform gradients. Then imagine you train this model. You gave it a tons of text and it learned to generate text. So actually the model became the language model. Why we did it in this assignment is to generate some text. So here what we do, we give it some prefix, we give it number of letters that we want to generate, we give it a trained network, vocabulary, and device. See, we initiate state and we put prefix into as a first output. Then we turn the network in a generation state. Get input is a lambda function definition that we will put to a network. See, get input, we pass it, get input as a forward function. Remember this parameter forward function? So it's end state. The state is initial state of the network. And then we generate the symbols. We append to a vocabulary a new symbols generated by network. See, we are appending to outputs like indexes of letters from our vocabulary. And then we transform them to tokens. We take these outputs are indexes, and then we take appropriate tokens by indexes from our vocabulary. So we return a word. So in this experiment, we used one hidden layer with width of 512. We initiated the network. We initiated its initial state, and we started generation. We generated 10 symbols, right? And we got what prefix? We gave it prefix. the prefix was time traveler. So the rest are generated. And you see the quality of generated text. It is horrible, right? Why it is horrible? Because we didn't train this network. We just initialized it and we used the default weights to generate something. Of course, we got random results, which is not satisfiable, right? So let's declare the training, and the training, let's train it for a few epochs. You, on the last hour lecture, you saw this training algorithm. But it is a bit different, and I will show you on the difference. So the difference is that you pass the network activation inside, between epochs. See, train with one epoch. So here you store metrics. See, you preserve state. The state is the parameter that is not lost until the training ends. Then you iterate over your x's and y's, like inputs and outputs. If you initialize a new state, so if the state is none, so if it's a first step, or you use random iteration, you initialize state, you use random sampling to initialize state. If not, you move it to device, and then you reshape it, you move to devices, and you predict something. You take a network, you pass like your inputs, your state, pay attention, and you generate some prediction. And the difference is that your network on every forward, it does something and it returns you its new state. Then you calculate loss, and then you update weights. The training loop looks like this. You select some loss function, you initialize math optimizer function, you use a generator function that declared before as a prediction function, and for number of epochs, you call one train epochs and you try to generate something. The perplexity is a difference from a ground truth labels from the predicted ones. And then you try to predict after training for 50, you generate 50 words. You train it for 500 epochs with learning rate 1. We plot here how the perplexity decreases. And you can see that, well, now it's something. There are at least a few words that are consistent. Yeah, but still, this is not the best, and it doesn't make much sense. And these are other attempts to train it more. Yeah, you can note that we forgot to a space here. And yeah, all of them contain mistakes. Takeaways. Neural network that uses recurrent computation for hidden states is called recurrent neural network. The hidden states of a recurrent neural network can capture historical information of the sequence up to the current time step. Your hidden state accumulates previous states, in other words. The number of RNN model parameters does not grow with the number of steps. Because your network remains the same architecturally, your number of weights remains the same. You only update the weights taking into account previous steps. And in this exercise, we used a character level language model using an RNN. Yeah, it works so-so. Then we can use perplexity to evaluate the quality of language models. Issues. You saw that the longer text we generate, the lower quality it has. Also, RNNs can capture like around 20 symbols and then they start losing context. It means they don't remember that was the context like 20 and 50 symbols before. If you have very long sentences, yeah, they will lose any sense without like after first few words. It happens due to vanishing gradients and exploding gradients. Vanishing gradients is when your gradients are less than 1, and your existing weights are multiplied by this coefficient, and hence your weights become, your gradients become smaller and smaller and smaller, and at some point they just not meaningful. They cannot change your weights anymore. Exploding gradients is when your mean of gradients is larger than 1. Then your weights are grow so much that they explode the type of a container. You want your gradients to be stable, like within 1. So these exploding gradients are easy to fix. Vanishing gradients are harder to fix. Exploding gradients are fixed easily with gradient clipping, like renormalization of gradients at each step. So when they start growing too much, you just rescale them and keep them in some range. Vanishing gradients is harder to deal with because you cannot just rescale them. Otherwise you will get exploding gradients from on other side, because some of your gradients will be okay, other ones will vanish. If you will try to fix the vanishing one, your okay gradients will explode, because this is a matrix of all the weights. So this is easy to fix. Now let's talk about how to fix vanishing gradients. To fix vanishing gradients, a number of improvements of recurrent neural network have been invented. One of them are GRU, or gated recurrent units. Gated recurrent unit, you can see it has more elements than a regular RNN. These elements, known as gates, are something that helps to keep vanishing gradients away. They help to keep more consistent gradients. You see the same picture that you saw before. See, this is activation and your neural network is here. Yeah, and here your hidden states and your inputs, and they are also concatenated. But there are a few new things. First, you have a reset gate and you have update gate. Update gate controls what parts of hidden state are updated and which are preserved. A reset gate, see, it's an interaction of your X and your hidden states. So this is a multiplication and a sigmoid activation. Sigmoid activation is 0 or 1, or it's a value very close to 0 or very close to 1, usually. So this gate actually mutes something and or allows something. Yeah, it's open or closed. Your reset gate controls what parts of previous hidden states are used to compute new content. This is an element-wise multiplication, so you can think of these gates as a mask on your weights. And remember, here you have weights. And this is a mask on the weights, which allows something and disallows something. So reset gates select useful parts of previous hidden state, and it is this and current input to compute new hidden state content. Hidden state with use of update gate simultaneously controlled what is kept from previous hidden state and what is updated to new hidden state content. So it's a combination of what should be remembered from inputs and what should be used from hidden states. And then you have the same, your network and activation function, but it is modified. Now see, we modify what we use to put to a neural network. Two output condition state. One more difference is that now we output activation. Activation this hidden state contains all of the tweaks and interaction of gates that we performed. These reset gate and update gate are also trainable networks. So there's two networks additional that are trained. They just filter inputs. But also pay attention, you have H with this weight. This is a raw candidate hidden states, calculated in the way we calculated it before. Here, remember we calculated hidden states by simple like concatenating inputs and previous hidden state. So this is your old hidden state and the new hidden state. Now, in more details, how your update gate acts. So update gate controls which parts of hidden state are updated and which are preserved. Update gate is a sigmoid activation, and you input there your inputs multiplied by matrix of WXZ. It's another set of weights. So you have weights here, plus hidden state. So your inputs plus hidden state multiplied by WHZ. This is another set of weights, plus B. Your Z will have zeros or ones in its cells. Your reset gate controls what parts of previous hidden state are used to compute new content. Again, WXR and WHR are additional sets of weights as well as BR. Again, you reuse your inputs XT, you multiply XT by this set of new weights, you add your hidden state multiplied by new weights plus H. Then your candidate, your hidden state candidate, this H from T, is a hypertangents activation with inputs, like irregular inputs of XT, WXH, XT, WXH, plus your reset gate results, those that will be the matrix of zeros and one, multiplied per your hidden state. So this gate will select which elements of hidden state, previous hidden state, to use in this iteration of training of your main hidden state. And then plus bias. This is step number one. You calculate candidate hidden state with using only reset gate. See what happens next. Then calculating a hidden state candidate, which you output here, you use this to calculate the hidden state that you compare with your target label. You use update gate, see update gate multiplied by previous hidden state plus 1 minus update gate multiplied by candidate hidden state that was calculated using a reset gate. So this formula says you, hey, try to take some other elements from previous hidden states that must be updated, or the ones that not will be updated, take them from this hidden state and reset, because this hidden state candidate was calculated using the reset gate. So here you remembered elements to reset. So this value will be to some extent from elements that of the previous hidden state that has been updated, and some elements preserved in their raw form by resetting values. So this is a mechanism how to propagate further information from longer sequences. Because see, now it's more deliberately selects elements to preserve or to update or to reset. with these new sets of weights. Altogether, GRU will look like this. Yeah? You first calculate update gate weights, and these are new sets of weights. Then you calculate reset gate. Then you calculate hidden state candidate, and then you calculate your new hidden state, which is your predicted output y hat. Here's the GRU definition of a single cell. Yeah, remember the GRU works like this. You have this single cell, and then you repeat on every sequence element, all of this. See how many weights you have, parameters. You have WXZ, WHZ, WXR, WHR, WXH, WHH, WHQ, and corresponding biases. The rest is the same. You have a hidden state. You iterate over elements in your sequence. You calculate update gate, reset gate. You calculate hidden state candidate. You calculate hidden state. When you have hidden state, you multiply it by output weights, and you get your output, predicted output y hat. You compare this y hat with ground truth labels to calculate loss. Okay? And here you just concatenate your outputs. Yeah, remember that all the recurrent models, they at each step they return, and this is very important. They return predictions wise, and they return hidden state at this step. Takeaways: GRU has reset and update gates in addition to usual RNNs. Reset gates helps to capture short-term dependencies in sequences. Update gates help to capture long-term dependencies in sequences. Now, LSTM. Historically, LSTM was first. LSTM was invented in 2010. GRU was 2014. So historically, GRU is older, but it has less weights. LSTM is more complicated than GRU. It have 3 gates. It has forget gate, input gate, and output gate, as opposed to GRU with 2 gates, update gate and reset gate. So it is even more complicated. LSTM, like forget gate, controls what is kept and what is forgotten from previous step. Input gate, this one, controls what parts of the new cell content are written to the cell, like what access, and rewrite all the activations. Output gate, this one, controls what parts of cell are output to hidden state and which are not. New cell content, this is the new content to be written to the cell. This is an activation candidate. Now let's put them all together. So this, like a first gate, forget gate, input gate, and output gate. And this is this thing computes a new cell content. Like this is your main neural network. You have 1, 2, 3, 4, 5 neural networks here. So this is element-wise multiplication. Here you multiply the trained forget gate to previous active hidden state. So you select which elements of this hidden state to use. Here you do the same, but for access input gate. You use this gate selects which elements of input to use, and then they form activation, like a hidden state candidate. Then it goes through a third gate, output gate. Output gates, but next. Here you take some content from previous state and you write some context that passed this gate. So now you have a combination of old weights information and some of the new information. Now this product or this sum of products, it goes to your final neural network where your output gates are filtered one more time. And in this way, you output row activation and activation candidate. If we compare LSTM and GRU, you can see that GRU have a update gate, forget gate, and update gate are combined. Input gate and forget gate, they are shared. And also the output of a cell state is combined with a hidden state candidate. LSTM outputs them separately. It outputs cell state and it outputs a raw output. So LSTM passes a raw output to the next LSTM cell. It uses the same value of raw output to compute loss by comparing it to the ground truth. Which one of them works better? It depends, and which one to use depends on the amount of data that you have. If you have less data, I advise you to use GRU. If you have more data, it's better to use LSTM because LSTM has more weights and more naturally tends to overfit if you have lack of data. Here are all the computations denoted. Forget gate. See, this is one set of weights, another set of weights and bias. Forget gate controls what is kept and what is forgotten from previous hidden state. So literally those are zeros and ones multiplied as a mask to the previous cell state. Input gate controls what parts of the new cell content are written to the cell. So here you calculated, see it's X multiplied by set of weights for X. So you filter something for inputs plus hidden state multiplied by its weights, yeah, as opposed to this one. So it selects what to input, in other words. And the output gate, again, it's a sigmoid, so those are matrix of zeros and one, is a product of raw inputs by a new set of weights plus, again, activation multiplied by its own set of weights plus biases. So those weights are trained separately, gates. Now here, this is a new content to be written to the cell. Candidate memory is a whole new hidden state that is like considered to be the main memory candidate. And those are new weights. So this input gate will erase something. The forget gate will erase something from this candidate, and the input gates will write something to its candidate. And here is how the final new memory or hidden state is calculated. So when you have this new memory, now you multiply this new memory by output gate. And it will like nullify something and leave something in its state. In this way, you will get a new hidden state. Gates, they act only as a masks. See F, forget gate, element-wise multiplication by C, plus I input element-wise multiplication by a candidate. So C, T-1 is old memory, CT is a new. So something we will take old, something we will take new, and then we will, add it up here. We will get C. We will pass C to the next step of ourselves. See, so this is a C from previous LSTM cell. But we also use this C to calculate our new hidden state, which is our input and Y hat. It's our prediction, right? Also. And it's another gate output gate, which acts as a mask. Yeah, output gate is zeros and ones. Multiplied as a mask by activation of our candidate memory. If we review its implementation, it will become a little bit simpler. As you see, we have much more parameters here. We have WXY, WHY, and all of the other things that are parts of input, output, and forget gates. Now our state consists of two elements, yeah, as opposed to GRU. In GRU, your state was made of one set of weights. But the LSTM now have two state components. It's a hidden state and C. And you have more gates. You first calculate the states of gates. Yeah, the sigmoid returns you 0 or 1. So you input all of this. It's your X inputs. H, hidden state biases. Those are lowered parameters. And you will get these masks. IFO, think of them as matrix, I don't know, 5 by 5. Some will be zeros, some were ones. And then they are used, and then you calculate update hidden state candidate. The same you did in RNNs. You have weights for inputs, you have weights for hidden state, and you calculate this candidate. It's like what if I update everything, right? And these gates are made to preserve this element from updating everything, because we don't want to lose our gradients. We don't want to lose information from previous steps. So now this update everything data is multiplied by input gate. Yeah, it says, okay, let's select elements that are relevant for update and let's mute other ones. The other thing does this. The C is previous cell state, and we multiply it by forget state. Here we decide which elements from previous state to forget. And the combination what to forget and what to update gives us C, new cell state. We use this new cell state, we multiply it by O. O is the output gate state. Again, think of it as matrix 5 by 5 with zeros and 1. Yeah, it will like nullify some elements and leave some elements. Yeah, if we select relevant elements from this cell state, we will get new hidden state. And then we make our prediction from this new hidden state by multiplying it by corresponding set of weights and biases. Here we have Y hat, our prediction candidate that we will further compare with ground truth and compute loss. Here we return to the next step of LSTM. Our outputs, Y hat, and our hidden state and cell state. Takeaways. LSTMs have three types of gates: input gates, forget gates, and output gates that control the flow of information. They decide what to update, what to forget, yeah, and what to output. The hidden layer output of LSTM includes the hidden state H and memory C cells. Only the hidden states is passed to the output layer. It means here, the output layer, what we compare with Y. The memory cell is internal. Internal means they're used only for training of the network. And LSTMs can alleviate vanishing and exploding gradients. The same as GRU. So GRU and LSTMs are improvements to recurrent neural network, the baseline, the vanilla architecture, trying to handle the vanishing gradient problem. Here you can see the references.